So I thought I would go through the 2018 Extension 2 exam that we just had a few weeks ago, because I'm sure some people are wondering how to do some of the questions, the ones that they couldn't do. And the solutions aren't out yet, so I apologize if I make any mistakes, because usually I check things over with the solutions, but not this time. Question 1. So this is from the formula sheet, and you can use this to work it out if you want. So we need to get it into that sort of form where there's no coefficient on the x squared. So what you could do is think of the 1 minus 4x squared as being 4 times a quarter minus x squared. And then we've got the square root of that. So you can split that up into the square root of 4, which is 2 times the square root of this. And then that quarter, since we want it in the form a squared, I might write it as a half squared. So we've got 1 on that. And then you've got like this 1 over 2 that you can pull out the front. And now it's in that form, so you can say that it's going to be half times arcsine of x over a, where a is a half. So x over a half is 2x. And that gives you b. The way that I did it, though, I find these a bit weird. The way that I thought about it was that I know that the derivative of arcsine x is 1 over root 1 minus x squared. And so I know that if I do arcsine of 2x, then instead of x being there, we're going to have 2x, and that'll give us that 4. So you get 1 over root 1 minus 4x squared. And then by the chain rule, you also have to multiply by the derivative of that, so you'll get that. And then I think of what do I need to do to this to compensate for that 2 and get rid of it, because there's no 2 here. So we do half, and then that gets rid of that. So that's my thought process when I do that kind of integral. But you can also do it using the thing on the formula sheet. Question 2. I'm just going to rearrange this a bit. So it's like 4y squared is 9x squared minus 36. Now, if you want to think about the limit as x gets really big, which is what the asymptote is, the way that I think about it is like if you imagine x is, say, 1,000, then this is 9 million. And the 36 doesn't really matter much anymore because it's really tiny in comparison to this. So in the limit as x gets really big, you can basically just ignore that and just imagine that that's the equation. So that would give you, if you just square root both sides, you get 2y is plus or minus 3x. 2y equals plus or minus 3 on 2x, which is c. Question 3. So there are 2 main methods that you can do this one. One is just to think about what the sum and products of all the roots is going to be. So just looking at this, alpha plus beta plus gamma is going to be -2. If I get confused about which ones are negative and which ones are positive, I always go back to doing like this is going to be the same as that, and then think about expanding that. So for the x squared coefficient, you're going to get like that negative alpha times the x, which means that this is actually like negative alpha minus beta minus gamma is the 2. Anyway, so that is -2. And that one's going to be +5, because when we do 2 of them together, the negatives cancel. And then we've got alpha, beta, gamma is going to be equal to +1, so the opposite of that, because you get negative alpha times negative beta times negative gamma, which gives you negative alpha, beta, gamma. It's the -1. So we know that those are true. And then what we need to do to work out the coefficients of this other cubic equation is work out, what's the sum of these and the product of these and sum of the products So we want to know what is 1 on alpha plus 1 on beta plus 1 on gamma, and what is 1 on alpha beta, so like the product of two of them. What is that, and what is that one? So let's think about that. This one's pretty easy because it's just 1 over that, so that's just 1. This one, if we make a common denominator of alpha, beta, gamma, we would have to multiply this one by gamma on top and bottom, so it's going to be gamma plus alpha plus beta. Oh, that was a weird beta. So that's just the -2 over the 1. So that's -2. With this one, we can do the same thing. We can make a common denominator of alpha, beta, gamma, and then it's going to be beta gamma plus alpha gamma plus alpha beta. So that's that one on 1, so just 5. And then we need to think about whether things are going to be positive or negative. So the cubic is going to be like x plus 1 on alpha, so x minus the root times x plus 1 on beta, x plus 1 on gamma. So all the coefficients are just going to be the positive versions of these. So it's going to be x cubed plus the sum, 5x squared, and that one, and plus 1 equals 0. So that's D. Another way that you can do it is you can think of like, so if like x is alpha and beta and gamma when you solve that, and we want a cubic equation that has those roots, what we're looking for is one with some other variable equals -1 on x, so that when x is alpha, that works for y being -1 on alpha. So we can solve that for x, and then plug that into this equation, and then manipulate it until we get a cubic. And we know that the solutions of that cubic, the cubic in y, are going to be those, because we know that y is that, and the solutions of this one are alpha, beta, gamma. That explanation never makes sense when I say it, but somehow it makes sense in my head. Anyway, I hope it made sense to you. So we need to plug that into here. So we get -1 on y cubed is -1 on y cubed. And then we've got +2 times -1 on y squared. So that those negatives are going to cancel, and we get 2 on y squared. And then we've got 5 times -1 on y, so -5 on y, and -1 equals 0. And then we want to turn this into a normal cubic, so we can just multiply both sides of the equation by y cubed. -1 plus 2y minus 5y squared minus y cubed equals 0. And then we want to make that coefficient 1, so let's multiply everything by -1 and change the order around. So we're going to get a positive y cubed, positive 5y squared, -2y, and positive 1 equals 0. So that's D as well, if you do it in terms of x rather than y. Question 4. The way that I thought about this one was that since we've just got square root here and not plus or minus square root, we're only going to get positive y values, because this is always a positive number. So we're going to get 1 over a positive number. So y is always positive. That rules out B and D, because they have bits with negative y values. Okay, and then we just need to worry about whether it's A or C. So big difference between these is what happens when x gets bigger and bigger, because here it's heading off to infinity, but here it's heading off to 0. So let's think about that. When x is really big, you're going to get big number on the denominator here, so 1 over that is going to be a really small number. So we're expecting it to do that sort of thing rather than shooting off like that. So let's see. Question 5. So I know that a lot of students have issues with visualizing what that shape's going to look like and what that has to do with the integral. So I wanted to give you guys a proper 3D model of what this looks like. So here's our function. What we want to do is imagine this shape swinging around that axis and like cutting out a 3D shape. So that's going to look like this. So that's the shape that we want to work out the volume of. Kind of a trumpet thing. And the way that we work out that volume is we imagine cutting that shape up into disks like this. And we can work out the volume of each individual disk. I'm just going to pull this out so that we can look at it. So this disk has a thickness of, whatever we choose it to be. I'll just call that delta x, meaning the change in x. I've made 10 disks here, so that would be 4 divided by 10 in this case. And let's think about what the radius of that disk is going to be. So the y-coordinate here was e to the 3x, but the y-coordinate of the center is at -1. So you can imagine it goes up. We've got a distance of 1 there, and then e to the 3x. So that's going to be e to the 3x plus 1. And then this is just a cylinder, so the volume is going to be pi times the radius squared times the thickness or the height of the cylinder. And then for the total volume of the whole shape, we just add all these up. So the sum of all of those. So that's for a finite number of disks, which would give you a good approximation for the volume of the shape. But the true volume of the shape, you can get that by doing like an infinite number of disks. So the limit of this as the number of disks increases and delta x decreases. So the notation for that is just, instead of sigma for sum, it's long s for sum. And instead of having delta x, we have dx, which just means a really, really tiny delta x. Now, I think it's one of the coolest mathematical facts that you can do this infinite sum by doing the antiderivative. That's the fundamental theorem of calculus. And I really didn't appreciate it when I was in high school because I just learnt that that was antiderivative, like that's how I was introduced to integrals. And so I think that a lot of people don't realize that that doesn't mean antiderivative. It is just an infinite sum that happens to be the antiderivative. And that is actually a really cool fact. But anyway, so, and of course x runs from 0 to 4. So I should put that in. And then you can pull the pi out the front because that's just a constant. And then we get that. So that is A. Now, I don't know about you, but I'm not happy with a multiple choice question until I can see why the other answers are wrong. So these two are wrong because they've got -1 instead of +1. You can see you've got e to the 3x there, and that distance is 1, so that radius is going to be the sum of those two, not e to the 3x minus 1. Okay, what about B? Well, that's actually what you would get if you rotated the shape around the y-axis instead of this axis. So let's take a look at what would happen then. So imagine taking this whole thing and rotating it around the y-axis instead. So just picture that in your mind. That's going to look like this. So that shape, you can work out that volume by doing a series of cylindrical shells like this. So let me just pull out one of these shells so that we can think about what the volume of that is. So the way that I like to think about the volume of one of these shells is I imagine cutting it down that line and folding it out, which is going to look like this. So that dimension there is our delta x, whatever change in x we choose. and the height is the e to the 3x plus 1 if we're taking it from that line up. And this distance is just the circumference of the shell. So 2 pi times the radius. And the radius was just x. So the volume of that flattened cylindrical shell is 2 pi x times e to the 3x plus 1 times the delta x. And again, if we want to work out the total volume, you just add all those up. And then if we're thinking about the limit as delta x tends to 0, or as the number of cylindrical shells increases, we just write long S instead of sigma. And dx instead of delta x. And x is running from 0 to 4. So that would give you the volume of that shape. Which is why B is wrong, because it's rotated around the y-axis rather than the line y equals -1. And I just wanted to mention that I don't actually memorize these sorts of things as a formula, like this one's for disks and this one's for cylindrical shells and this one's for rotating around the y-axis and so on. I actually picture the whole thing and actually try to work out, okay, what would the volume of one disk be, and so on. I think that makes you more adaptable with these kinds of questions. Like, if you're just sort of memorizing stuff, you can get thrown by things where it's rotating around this line instead of around the x-axis. So I think it's better to be able to visualize that stuff and kind of derive everything anew, even if it takes a little bit longer, because it does make you more adaptable. Question 6. So with this one, you can just put those values into your calculator, if you have a calculator that can handle complex numbers, and raise it to the power 6. So you'll see that A works. When you raise it to the power 6, you get I. So that means that one's correct. If you didn't have a calculator that can handle complex numbers, what you can do is think about the modulus and argument of each of these. So with these two, if you work out the modulus, it's going to be that, which is 2. So that means when we raise it to the power 6, the modulus is going to be 2 to the 6, when we actually want the modulus to be 1, because that's the modulus of I. So we can rule out those two. These ones have the right modulus of 1. But let's think about their arguments, their angles. So this one is at here. That's where A is, and B is over here. So that one, if you like, you can think of this as that's going to be 135 degrees. Probably should be working in radians, but that's all right. And that one's 225. And you can do that times 6 on your calculator if you like. 135 times 6, and then you can take off 720, so 2 revolutions, and that will give you hopefully 90 degrees. Yep. So that means 90 degrees is up here, so that's where I is. So that one's right. That one, if you work out the modulus of that, so 225 times 6, and then take off however many multiples of 360 you need. So for another 360, you get 270. So that'll be down here at -I. So A is definitely the right one. Question 7. So the way that I would think about this one is that this is Z minus -1 plus I, and that means the vector from that point to that point. So if you imagine that's sort of around there, and let's just pick a random Z. So it's saying the argument of Z, so that the direction of that has to be the same as the direction of this, which is from that point to Z. So we want those two arrows to be parallel and pointing in the same direction. Because if they're pointed in opposite directions, then the argument of this one is going to be like pi plus the argument of that one. So that's not going to work. So let's think about some of the differences between these diagrams. So some of the diagrams have points in this region and others don't. So let's think about if z is here, will that work? So argument of z is the direction of that. Argument of that is the direction of the vector from that point to z. So that works, because those arrows are both in the same direction, pointing the same way. So we should include points in that region. So we can rule out B, because it leaves those out, and C. Now let's look at the difference between A and D. D includes points up here, where A doesn't. So let's think about that. So if that's our Z, then we're talking about the direction of that being the same as the direction of the vector from here to here, which also works. So those arrows are in the same direction. So points along there should be included, and they're not in A, so we can rule out A. So it must be D. Question 8. The way that I would think about this one is that if we want to graph the integral of this, then this graph represents the slope of the function we want. So let's think about what that's going to mean. Here we can see that the slope is positive because it's above the x-axis, and it's also increasing because it's going up. Like that point's higher than this point, therefore the slope must be bigger here than here on our graph of big F of x. So it's going to have positive slope in this region, but also increasing, so it's going to be going like that. And then for this region, we've still got a positive slope because we're still above the x-axis, but it's decreasing. So after point A, it's going to be still positive slope, but decreasing. And then we reach B, so that's A. We reach B, and the slope is 0. And then we've got negative slope that's also getting steeper because we're moving down here. Like the slope here is, maybe something like negative 0.1, and maybe here it's negative 1. So it's getting steeper negative until we reach C. And then the slope is still negative, but it's getting towards 0. So it's doing that kind of thing. We reach D, and we've got a slope of 0. And then we've got a positive slope again. So you can see that the concavity changes just at A and C. So that would be B. Question 9. The way that I would think about this one, since P and Q are imaginary, that means we can say let P equals I times C, where C is a real number, and Q equals I times D. And then we can rewrite these equations in terms of just real numbers. So let's think about this one. So we've got A squared times P squared is going to be negative C squared. And then you've got B squared times Q squared. Q squared is going to be negative D squared, so we're going to negative B squared D squared. And then on the right here, we've got 2AB times PQ, which is negative CD. So what I would do with an inequality like that is, let's move everything over one side. And I'll move these so that they become positive. So you get 0 less than or equal to. And then that's really good because we can factorize this. So this makes AC minus BD squared. And we know that any square of a real number is going to be greater than or equal to 0. So that works. So this equation is true. That means that we can rule out these two, which have the sign around the other way. Now let's think about the second equation. So we've got A squared B squared plus p squared q squared. Now p squared is negative c squared and q squared is negative d squared. So those two negatives are going to cancel. And we get plus c squared d squared. And it's saying that's less than or equal to 2ab times pq, which is going to be negative cd. So I would move that over to the left. And it's saying that's less than or equal to 0. So let's factorize that. That is ab plus cd squared. Now that's not going to work because that should be positive or greater than or equal to 0. And this one is saying it's less than or equal to 0. So this one is false. So it's B. Question 10. One way to think about this one is to try to graph both of these on the same axes. So sine x is like that. So those peaks, as well as the stationary points, is like these are the possible values of A. And so let's think about what g of x is going to look like. So this is x is pi on 2 there, which is like 1.5-ish. So x times sine x is going to be a bit higher. And here x is very small, so x times sine x is going to be lower. So it's sort of doing this. But let's think about what happens in the vicinity of this point. Over here, x is slightly bigger than it was here, which means that this point is going to be pushed up slightly more than this point was. So the peak might actually just be there instead of here. So what it looks like to me is that B is going to be a bit bigger than A for that point. You can verify that by doing the derivative and seeing, you'll see that the derivative of this at pi on 2 is positive, so it's still increasing there. And so it reaches the peak just a little bit later. Now we got to work out, so it's not B and it's not D, because B was a little bit bigger than A, but we got to decide which one of these two is right. So let's look at one with a negative A. So we could think about that one where A is negative pi on 2. And again, what you're going to get is that, so x here is around negative 1.5. So that's going to push this point to like bigger but also positive. So it's like there but flipped. So it's like up there. And if we look at a point just a little bit further, that's going to have a bigger x value or a more negative x value that's going to push that point just a little bit further up. So the peak is going to be there. And it's going to be like that. So that one has actually, the B is less than A because it's more negative. But you could say for that the absolute value is going to be greater than the absolute value of A. And that was true for this one as well. Except they've done it the other way around. So, C. Alright, I hope that those explanations made sense to you guys, and that I didn't get any wrong, and that you didn't get any wrong if you just did your exams. Next time I'll be doing question 11, so once that's uploaded, that'll appear here. So stay tuned for that one.